Hello and welcome to my YouTube channel. Today I'll be talking about Thevenin's theorem. I've already talked about superposition theorem, so you can watch it in the other video. If you're interested in superposition theorem, I've already done a video on that one. But today's one is on Thevenin's theorem. And Thevenin's theorem says that a circuit diagram, that is a linear active circuit diagram, can be replaced by an equivalent circuit consisting of a voltage source in series with a resistor. The voltage source is referred to as Thevenin's voltage, and then the resistance is referred to as Thevenin's equivalent resistance. So what that means is that if you have a linear circuit, a linear active circuit, you can convert that circuit diagram to just a voltage in series with a resistor. That voltage is referred to as Thevenin's voltage, and the resistance is referred to as Thevenin's equivalent resistance. Now, how do we actually make sense of this theorem, right? First, we have to understand what we mean by linear active circuit, right? You can think about this as an example. So I have an example here on the board. For example, imagine you want to light up a light bulb. So you go to the shop, you buy a 1.5 volts battery, and the battery is having some internal resistance of 0.5 ohms. And you connect it to the light bulb. It lights up, right? It runs it up for some time. Then after some time, then the brightness starts to reduce. Now, you want, in order to boost up the brightness of the light bulb, then you add a 2 amps current source, and then you also include the fact that it's also having an internal resistance of 1 ohm. This is just an example, right? So you can see that with this simple circuit diagram that we are looking at, you can see that we have our load. Our load here is the light bulb. That is the important component in the circuit diagram, right? Because it's that resistor which takes the current from the voltage sources and then convert it into light energy. So that is our load. Now, in order to apply Thevenin's theorem, we have to divide the circuit diagram into two. All right, we have our load, which is a light bulb as in the case of this example, and then the load part of the circuit diagram is referred to as the linear active circuit. So when it comes to the Thevenin's equivalent circuit, it means that our work is going to be focused on the linear active circuit. It is that circuit that we have to we have to replace by a voltage in series with a resistor, right? So the whole of this, we can just refer to it as a linear active circuit because it can be any circuit diagram, right? You can have a circuit diagram whereby the structure will be different to this one here. So we can have a linear circuit, a linear active circuit, and then you can replace it by Thevenin's equivalent voltage. We have VTH in series with RTH. Now, how do we determine VTH, right? Thevenin's equivalent, Thevenin's voltage? Thevenin's voltage is actually the open circuit voltage. What that means is that if we were to move the load, from this circuit diagram, this example, as you can see, by doing this, you now have an open circuit. So you can add the terminal, all right? You add plus and negative here. So you have an open circuit. This open circuit that we have here, the voltage across the terminal, you can see terminal A and B. is what we refer to as the open circuit voltage. So you can see we have open circuit voltage, which is going to be the voltage across terminal A and B, right? And that voltage is also what we refer to as what? Thevenin's what? Voltage, right? So this is also our Thevenin's voltage. Now, when it comes to finding Thevenin's equivalent resistance, it is simple, the equivalent resistance when all independent sources are turned off, right? So here you go to back to your linear active circuit. You look at the independent sources in the circuit diagram and you turn off all of them, right? So you can see here, I have this example. If I want to turn off 1.5 volts, that means you connect a wire, you show circuit there, voltage. And when it comes to the current source here, how do we turn it off? By removing the current source so that it becomes open, right? By turning off all independent sources, you can see now we have only resistors in this circuit diagram. Then you calculate the equivalent resistance of this circuit diagram. That equivalent resistance that you get becomes Thevenin's equivalent resistance. So you can see here, this is on here, you can see this 1 ohm and the 0.5 ohm, they are going to be in parallel. So the equivalent resistance here becomes the Thevenin's equivalent resistance. Now after getting VTH and RTH, we now have our simplified circuit, right? That's just the objectives of what Thevenin's theorem is, to simplify a complex circuit so that you can reduce it to just a voltage in series with a resistor. And once we are done with that, we can now add our load, which we removed earlier, our load resistor. And you can see here it's now a simple circuit, right? Now you can find the current passing through the load resistor, right? By using a network reduction method, the current here will just be equals to the VTH over the sum of RTH and then the load resistor RL. This is how you apply Thevenin's theorem. I'm going to be providing an example and then we see how we can better apply Thevenin's theorem. Here, I have an example on the board. And I'm going to try and use Thevenin's theorem to solve for the current passing through the load resistor area. When it comes to this, we try and then find the equivalent, find Thevenin's equivalent circuit from this circuit diagram, right? And from what I said earlier on, Thevenin's equivalent circuit is the voltage in series with a resistor. And that voltage is what we refer to as Thevenin's voltage. And then the resistance is referred to as Thevenin's equivalent resistance. Now, our aim is now to find VTH and RTH from the linear active circuit. So we have to try and get our linear active circuit. Now, how do we get it? By removing the load, right? So we come here, we remove the load from the circuit diagram. So now we have an open circuit here. And we can add the terminal. We have an open circuit. So we stand here and look the voltage, right, across terminal A and B, which is just going to be the voltage at this point is going to be the open circuit voltage, which is also the same as the Thevenin's voltage. So we are standing like this and we are looking at the open space. You can see that we can see the R2, right? That means the voltage across the terminals, you can see it's all R2 there, right? That means the voltage across R2 becomes our Thevenin's voltage. So as you can see here, then we now try to find the voltage across R2, and that simply is going to be equals to equals R2 over R1 plus R2 times Vs. Why? Because we look at this in terms of what our voltage source here. If there's a current coming from the voltage source, it's to pass, then here's a node, you reach this node. That because here is open circuit, no current will pass to would flow through the R3. So all the current will pass to R2, then from there R1. That means R1 and R2, since there's the same current passing through them, that means they are in series. So we just have a voltage source in series with two resistors, R1 and R2. Then we can just go ahead and use voltage divided to get the voltage across R2, which is going to equal the resistor, which is R2, over this equivalent resistance of the resistors in series. So that's R1 plus R2, then times the voltage source, which is what just here Vs. Now, when it comes to finding RTH, it is the equivalent resistance of the linear active circuit when all independent sources are turned off. So if you look at our linear active circuit, we can clearly see we have Vs, which is the voltage source. I'm going to turn it off. Come here, we short circuit the voltage by connecting a wire. So I've connected the wire. The voltage source has now been short circuited. Now, we look at the circuit diagram and try to find the equivalent resistance. So if we look carefully, you can see now R1 and R2 are in parallel. Then after that, and series what R3. So we get the equivalent resistance for R1 and R2. That is going to be the what? The sum, the product over the sum, right? So we have R1 times R2 over R1 plus R2. Then in series with R3, so plus R3. This will give us the RTH. Now that we have VTH and RTH, we have now our equivalent circuit. Then we connect the load resistor RL and then get the current passing through the load resistor. And that is going to be equal to VTH over RTH plus RL, right? So this becomes a simple circuit. So you can just see that RTH and RL are in series. So we get the equivalent resistance of that will be RTH plus R. Then we have the VTH. So this is how you apply Thevenin's theorem. If you want to see more videos on circuit diagram, make sure that you subscribe to this channel. I'm going to be solving a lot of questions on circuit diagrams. See you in the next video. Bye-bye.